Whoopsie. That's an E, not an I. Gel permeation, also called size exclusion. Chromatography, right? So GPC, gel permeation, size exclusion, SEC. If you are in polymers, maybe you've talked about size exclusion chromatography, yeah? And so in size exclusion, the way that it works is you have these large beads that have some pathways through them, right? They're kind of like a pumice stone, right, or something like that, where you've got sort of this large chunk of something, but it has lots of holes and wigglies through it. And if I were on a whiteboard, I could erase all these so they're actually open, but here it erases the whole line. So you're just going to have to understand that these are all connected to one another. Right? And so, you know, you've got your column is packed with these things, right? And with size exclusion, you're going to have some tiny little paths, right? But you're also going to have some big old wide paths. And it turns out that the larger the particle is, the fewer options it has as it goes through the column, right? Because there's only a certain number of paths that are large enough for those largest analytes to come through. And so if we have our different analytes here, this big guy can only fit in a few places. Whereas if we go a size smaller, right, he can go through some others as well as through the large ones, right? Oops. And then if we have yet another one, smaller, he can go into these tiniest little holes as well as through all these big ones. And so the larger the analyte, the fewer possible paths. And so they elute first. You know, if you think about an 18-wheeler, right? He can't go through all the side roads because they have these bridges that are too short for him. And so your dad can take the car on all the side roads, and it takes twice as long to get there because he's going on all these little twisty turny roads, and the semi truck gets there first because he has to go on these main 4-lane highways. And so the larger analytes will elute out first, and of course the smaller analytes I'm going to use the word meander. All right, sort of wander through the column. And so they elute last. When we talk about size exclusion chromatography, there is a way that we can sort of tell based on those retention times what the size of one of those particles is, what the relative size is based on how well or how quickly, sorry, they come through. And that ratio, the ratio of the time that it will elute is called KO. And KO is equal to the the retention volume, right? And so we think about retention time a lot, and we can relate retention volume and retention time if we know the flow rate and all that stuff. But VR is the retention volume. So how much volume do we have to push through in order to get out our particular analyte? Minus VE, which is the volume of the mobile phase outside of all these little tiny pores, right? And so VE, I'm going to make that purple. And so VE is all this volume that's outside outside the actual spheres, outside the actual material, right? And then on the denominator, we've got VM, which is the total volume of the mobile phase, including inside all those pores, minus VE again. And so VR, the retention volume, again, that's like retention time, but a volume. VE is what's called the excluded volume. And that's outside the pores. And then VM is the mobile phase volume. Which is everything, it's VE plus VP, if you want to think about it that way. The excluded volume plus the volume that's actually inside the pores. So maybe I'll put a total mobile phase volume. Okay. Now in GPC, usually the excluded and the total volume are known values, right? And so just like we talked a little bit about the volume of the stationary phase and the volume of the mobile phase in the previous, in that partition chromatography where we just knew about the polarity. Similarly, on these kinds of columns, that excluded volume and the total mobile phase volume are known values. And so you just have to do your experiment and figure out what the retention volume is. These numbers should all be between 0 and 1. The retention volume will only be equal to the mobile phase volume if it takes, if it takes every possible path through that solid support, right? The longest possible path through that support. So it would be the very, very smallest analytes would be 1. The very largest analytes would be closer to 0. Okay. If you're doing this for polymer studies, right, you would have a certain column, you'd have some known compounds, you'd make yourself a calibration curve. You would say, okay, I have this molecule, this polymer has a molar molecular weight of 40,000, and it has a K naught of, or K0, a K0 of 0.7. This one is 100,000, and it has a K0 of 0.5. And this one is 1,000,000, and it has a K0 of 0.2, right? And you'd make that curve, and then you could analyze your unknown. And as long as it's the same type of polymer, then you can just plot it on that chart and figure out roughly the size of your polymer, that particular size distribution for that polymer sample. One of the more common detectors in GPC is a laser detector, and essentially the larger particles will deflect the laser more, and so it's more scattering the larger your particles are. and so you actually get less light through for larger particles. You know, we won't talk about that too much, but maybe you've heard about that in polymer. Okay. All right. So on to the instrumentation. When we talk about HPL, when we talk about liquid chromatography, that's the title of this chapter. Almost always we're going to talk about high performance or high pressure liquid chromatography, right? HPLC. Because that's almost exclusively what's used in real labs for analytical work. There's also sort of prep work that uses flash chromatography, where you just have enormous amounts of stationary phase and you just push your sample through it very quickly, flash chromatography, to get a preliminary separation. Again, that's not an analytical technique, that's just a sort of quick and dirty separation. So we're going to talk about HPLC because that is, again, by far the most common variety that we'll see. In this particular example from our textbook, they have 3 options for mobile phases, right? And so remember, we mix these if we're going to do some sort of gradient elution. And the way that those are mixed are in these mixing valves, right? That's my cat. You set these valves at certain ratios, and so they pull a certain amount from each mobile phase reservoir, and then they're all mixed together before they go into the pump. These pumps are these pumps operate in a, sorry, they are usually sort of a double pump, in the sense that if you had just a single pump, think about like a piston in a car engine or something that's pumping, or even if you just want to think about, you know, a syringe, I'm going to pull some liquid from the mixer and I'm going to push it into the HPLC. I'm going to pull some liquid from the mixer and push it into the HPLC. You can imagine that if that were really how things worked, you know, pull it from a reservoir and push it into the instrument, that you'd have these pressure spikes every time that it was pushing into the instrument, and these pressure dips when it was not, right, when it was pulling from the reservoir. And so if you have one pump, your pressure curve, so I'm going to put pressure versus time, right? If you had one pump, your pressure curve would look something like this. Sorry about that at the end there. And so what they do is they often pair 2 pumps together that are exactly opposite each other. And so overall, you get a pretty constant pressure over time, right? This sample injection port we'll talk about on the next slide, right? And the auto sampler, you know, that's something that some have and some don't. The column is often enclosed, right? And so remember that for this affinity chromatography, for affinity chromatography and for the partition chromatography, that's the word I couldn't think of on Friday, for our polarity stuff, right? When we're talking about polar versus non-polar, we call that partition chromatography. For both of those, we have that distribution constant, right? How much of it's in the mobile phase, how much of it's in the stationary phase. And anytime we have an equilibrium constant, it depends a lot on pressure. Only if it's gases do equilibrium constants change for pressure.
like moles, the coefficient, the stoichiometry?
So when you talk about Arrhenius equation, um, you can take a certain equilibrium constant at one temperature and change it to see what the equilibrium constant would be like at a different temperature, because they change based on temperature. Um, so for a given system, KD wouldn't change. Um, if we had a smaller number of moles or a greater number of moles, right? As long as it's the same system, KD is a constant. Um, the pressure does affect it if it's a gas, but temperature is one of the biggest things, right? This is easier to think about in a gas situation, but it's more, things are more likely to be in the gas phase if they're hotter, and so the temperature increase and the temperature change is much more noticeable in gas chromatography than it is in liquid chromatography. But we want to maintain a set temperature so that our KD is constant throughout the length of our analysis. And so this column is in a little oven, right? And that oven is just held at a constant temperature. For, I would say probably 70% of analyses, that oven temperature is 30 or 35 degrees. It's just above room temperature to the point where the oven can maintain something constant and the temperature of the room doesn't really affect it. And so this is because those distribution coefficients depend on temperature. Okay. The detectors on HPLC are almost always flow-through detectors, right? Where the sample is flowing out of the column and it actually passes all the way through the detector and then it goes out. Now, they're just having sort of collection, generally speaking, out here. And so this could be a waste container, right? Or if you're separating and you really care about what you're separating, you could recollect your sample. And those of you that did columns this summer, you know that you could collect fractions, right? Where you inject a few microliters, but you're going to get off a few milliliters. Most of that's going to be mobile phase, but if you had lots of components, they'd be separated out, and you'd collect, say, a quarter of a milliliter in each sample. And so you'd have these, maybe you'd have 10 or 12 different fractions of your sample. And each fraction would contain a different component, or maybe one component was split over two fractions or something, but they're separated from one another. And so you can recollect those, and that's a way to, if you have a very precious sample or something like that. Okay, so let's talk a little bit more about this sample injection port. Just like in GC, which we talked about a couple weeks ago, where that needle moves crazy fast because we want a small volume injected onto the column. Same thing in HPLC. We want a small volume and we want the same volume every time. And so the way that an HPLC injector works, or inlet works, is that you see this little, they're showing it as a wavy line, this sample loop. What happens is you inject into the instrument and it flows through. I'm going to change colors real quick. It flows through. It fills up this sample loop and it goes out to the waste. Okay? And so whatever is sort of whatever's caught in that sample loop is what will go onto the column. Notice that this position changes, right? And so we rotate this whole mechanism. And so we've still got, let me draw it in here. We've still got our sample stuck in that sample loop, but now it's isolated. And as our mobile phase comes through from the pump into the loop, it's going to start pushing that little bit of sample through. Right? And so this is how we have a very well-defined sample volume that doesn't diffuse into the mobile phase very quickly. Right? It's sort of like, have any of you ever made Jello worms? So if you have like a piece of Jello and then you stick a straw in it, and then you pull the straw out, right? You have this nice little Jello worm, and then you can blow it at your little brother. And the Jello worm in that example would be your sample, right? And then the air that you're blowing at your little brother is your mobile phase, right? And so it pushes that sample through the straw, but you get a set amount of sample each time because your Jello cube is only 1.25 inches thick or whatever. Sometimes I understand my analogies are not the best, but I try. Okay. And so why do we do this, right? We get a set volume every time. If we do it this way, then we're reducing the amount of diffusion that takes place during the injection. Right? You can imagine that if we were injecting while the mobile phase was flowing, that we would have a lot of mixing going on, right? In this case, the sample and the mobile phase do not mix, right? It's almost like you've got this little plug, right? That's just moving through the column. And this is exactly what we want. Remember, we talked Friday in the Van Dienter equation that longitudinal diffusion, that sort of interaction with the mobile phase, both before and after our initial plug of putting that sample on the column, we want to eliminate and reduce the amount of diffusion that takes place into the surrounding mobile phase. And so if we sort of eliminate their mixing at the beginning, right, then we can minimize that. That's a big source of diffusion to begin with. And so if we can eliminate it at the beginning, then we're going to be better off as we go down the road. Reduce the longitudinal diffusion. This was the B term in the Van Dienter equation. I was going to put VD, but that's probably not the best. Okay. All right. The last instrumentation piece for us to talk about, well, I'll talk about the pumps here a little bit. This is, these are flow valves, check valves. We think about them as one-way valves. Right? And so the pump here, right, this part here is really our pump in the dark color. Right? That's really our pump. When that piston is moving backwards, right, he's drawing liquid in from this side and from this side, right? He doesn't really care where he draws it from. But this little ball here prevents liquid from coming back in from the column, right? It's already passed that way. And instead of sucking that liquid back in, that ball gets sucked in and no liquid really gets past it. However, on this side, that ball moves out of the way, right? And so all the liquid from the mobile phase can come in and fill up this piston. Then when the piston goes down and we push liquid back out, we're going to push it both directions, right? Again, the pump doesn't really know. Here we're going to push this ball up against that opening so we don't push it back into the reservoir. We're going to push this ball out of the way so that it can go into the detector, or sorry, into the injector and the column. And again, you've got these two pumps that are working simultaneously so that you mitigate those pressure waves. In lots of instrumentation, there's also what's called a pulse damper. Right? And a pulse damper is, it's essentially a small reservoir after the pump that fills up, and as it fills up, it sort of reduces the effect of that change in pressure, right? You've got a lot of liquid, and that liquid gets a little pressurized in this pulse damper, right, as it's being pumped in there. And then you can, you know, as you're pumping in things, the pressure inside that pulse damper doesn't change a whole lot, and it has a flow restricted outlet that sort of maintains a pressure. So let me just draw a little box here. Right, we can think about it. So this would be from the pump, right? And inside our pulse damper, we're going to have some liquid. And then this outlet is a flow valve. And so what this does is, no matter the pressure that's coming in from the pump, right? So I'll say that this is a higher pressure from the pump. This flow valve has a set pressure that's going to be lower than the pump pressure. And so say you're pumping in there at, I don't know, 1 PSI, right? We don't really measure liquid pressures in PSI, but it works. At 1 PSI, that flow valve might be set to 0.9 PSI, right? What that's going to do is that as your pressure comes in, if it's coming in a little bit of a wave, right, that you don't have a constant 1 PSI, you'd set this to essentially the minimum of that pressure wave, so that it maintained pressure even if the pump didn't, right? So again, let me draw our little pressure versus time. This is how you can get away with only having one pump, right? Have a pulse damper. And so this would be your pressure there, right? That flow valve would be set to. And so, you know, the instrument doesn't really see that change in pressure due to the pump action. It just sees the overall pressure out of that flow valve. All right. So then it goes through the column. We already discussed the different types of stationary phases, right? So 2 detectors. By far the most common detector is just a UV vis. And in hindsight, I should have made this diagram a little bit bigger, but here it is. The way that this works is, you can see here it's been cast in like an acrylic, but you have your mobile phase coming in. I'm going to draw the path of the mobile phase. Right? It comes in this way, it goes down, and then it exits that way. By doing it this way, you have your optical path. Right, so that's the light. The red is the mobile phase. Okay. And so you have a set path length. Right? And I've sort of just covered it up with this long blue line, but in these little adapters here, you have some quartz windows. So I'm just going to sort of redraw it here. So again, our mobile phase is coming in and leaves. On each side of this container, this detector, you've got some quartz windows. Right? And you've got a set path length, and you know, usually it's on the order of 5 centimeters or something like that. This one, if I had to guess, looks a little bit longer, maybe 10, but I don't know. But you have a set path length, which remember is B from the Beer's law equation. And so this would be from the light source, right? And this would be out to the detector. Because we want to take pretty instantaneous readings, right? If it's flowing at 1 milliliter a minute, these capillaries are super tiny. And so, you know, they only hold like 10 microliters per centimeter or something crazy small like that. And so, you know, if you've got 10 centimeters, that's only 100 microliters or something. And so if you're flowing at a milliliter per minute, you're flowing through there 10 times every minute. Right? And so if you want to be able to catch all of your sample, you want to take these readings pretty quickly. And so quick knowledge check here. Which of our UV vis detectors gave us the fastest response time? We only really talked about 2, a PMT or a diode array. Which one of those?
Diode array.
Yeah, because we can take the whole spectrum in half a second, right? And so these are almost always diode array detectors. So that you can take the whole spectrum multiple times in a minute. Okay. There are a couple other types of detectors. I already talked a little bit about the laser, golly, I can't spell, about the laser diffraction, right? And so that's where you have your sample. So here's our mobile phase coming out. it goes through a small opening. And so we narrow it down, just like putting your thumb over the garden hose, right? It causes you to increase that pressure. And so you get this sort of jet stream of mobile phase. And you have a laser that hits it from the side with a detector. And if the larger the particles are, we're going to get more scattering. If we get more scattering, does more or less light hit the detector?
Less light.
That's right. Less light hits our detector. Okay. The last kind of detector that I'll talk about is a refractive index detector. And the way that this guy works this would be your sample in the mobile phase. This side would be pure mobile phase. Right. So after you do your mixing to get whatever mobile phase you're interested in, you'd have to split that so that the pure mobile phase without any sample in it goes to the detector, but also the mobile phase that goes through the injection loop and through the column also goes to the detector, right? And so as you're shining light through here, if there's no sample at that moment coming off the column, then really it's pure mobile phase on both sides, right? But as soon as a sample starts to come into that detector, now you've got this mobile phase with a little bit of sample in it, right? And so as the sample elutes, right, you have different refractive indices. Which changes the refraction, right? And so that changes the path of the light. And so, you've got a detector that's like a vertical line kind of detector. And so if the light normally shows up here, if there's a bit of sample, then that light might get diffracted and show up there, right? At that interface, you're going to see the difference in the refractive index show up because now, I've got these two different refractive indices that causes more more refraction. That changes the path of the light through the second material, right? This is for particularly viscous stuff, right? I mean, you have to have non-negligible changes in refractive index in order for this to be useful. That's not how you spell viscous. How do you spell viscous? It's close enough. This is for viscous samples or samples that have a relatively high refractive index. It doesn't have to be viscous necessarily, but that's usually what it's used for. Laser diffraction, remember, is used for GPC or SEC. What did you call it in polymer? GPC or size exclusion?
Size exclusion.
Okay. They're exactly the same thing. I don't know. It seems like different industries have taken different names for it. Okay. All right. That's the end of chapter 15 for us. Have you given any thought to my idea about having our final exam the Tuesday before Thanksgiving?